Hello everyone, welcome to today's session. For last few sessions, we have been studying about interference of light. This is the modification in the distribution of light energy due to superposition of two light waves. In today's session, we will see yet another phenomenon called diffraction, Huygens Fresnel theory, different types of diffraction and basic difference between interference and diffraction. This phenomenon is something that we observe in our day-to-day life. Have you ever opened the door of a dark room? We will notice bending of light. We are just opening door a little bit, but the light seemed to spread to more area. Okay, well, light is bending, but why? We have studied that light always travels in a straight path with constant speed 3 × 10⁸ meters per second. Then why the light is bending? The door acts as an obstacle in the path of light, therefore the light bends. This phenomenon of bending of waves around edge of an obstacle is called diffraction. We see this phenomenon in daily life. For instance, a cloud silver lining. This visual effect is a result of sunlight bending around the edge of the cloud. Corona around sun and celestial body is another example. These are ring of light around the sun or the moon that is formed when the sunlight or moonlight gets diffracted by small water vapors or ice crystals. Similarly, when light falls on the top of a CD, a part of it gets diffracted while some part of the light gets reflected and we see rainbow pattern. Hologram generate a 3D impression of the image by interference of diffracted sides of different versions of same image. This pattern falls on the holographic plate, giving us a three-dimensional experience. We can even observe diffraction in pond with small opening and in sound waves. So we may define diffraction as the bending of light around corners such that it spreads out and illuminates areas where a shadow is expected. This was first observed by an Italian mathematician and physicist, Francesco Maria Grimaldi, in 16th century. Since diffraction and interference occur simultaneously, it's hard to distinguish them. You may see how the light ray pass through small opening of width d. When opening is larger, diffraction effect is observed at greater distance. In general, diffraction of light becomes significant when the size of aperture become comparable to wavelength. Since visible light wavelength in the order of 400 to 700 nanometers, the size of aperture or obstacle must be in the order of angstrom to observe diffraction. This is one of the reasons diffraction is not readily apparent in case of light ray. We can give an explanation for diffraction using Huygens Fresnel theory. According to Huygens wave theory of light, each progressive wave produces secondary waves, the envelope of which forms secondary wavefront. Let S be a source of light, Mn be a small aperture and Xy be the screen placed behind the aperture. When light falls on the small aperture, we expect a portion of screen illuminated region and region above A. But, if we observe this in real life, the geometrical shadow region will not be completely dark. Just like that, if light falls on obstacle, we expect region AB to be completely dark and region above A and below be bright. Here too, shadows formed by obstacles are not sharp. Ac. To Huygens construction, if secondary waves drawn, we expect light in shadow region. This bending of light is diffraction. Similarly, shadow region due to obstacle will not be completely dark. If bulb light falls on a body, every point on surface of bulb form its own diffraction pattern. But, they overlap so that no single pattern is identified. In order to explain the resultant effect at an external point due to wavefront, August and Jean Fresnel combined Huygens wavelet with principle of interference. He point out the factors that decide the resultant effect. To explain this, he considered a monochromatic point source S. The spherical wavefront from source S falls on aperture Mn and the diffraction pattern falls in screen kept behind aperture. Point P on screen make angle theta with center C. So is perpendicular drawn to screen. The assumptions made by Fresnel were a wavefront can be divided large into no dot of strips or zones. Fresnel zone, a small area. Resultant effect at any point will depend on the combined effect of all secondary wavefront emanating from various zones. Effect at point due to particular zone depend upon distance of point from zone. Effect at point P depend on obliquity of point with reference to zone under consideration. Due to part of wavefront C, Effect will be maximum at O, and decrease with increase in obliquity. The resultant wave depend on obliquity factor that is directly proportional to 1 plus cos theta. At point O, theta equals 0 degrees, then 1 plus cos theta equals 2. That is the effect due to C will maximum at point O. We will get a central maximum at point O. At theta 90 degrees, 1 plus cos theta equals 1, the effect 1/2 as that at point O. At theta equals 180 degrees, obliquity factor 1 plus cos theta equals 0. Indicate no back wave. Even though interference and diffraction are similar in certain aspects, there are differences too. The differences between them are pointed out here. Interference is the phenomenon in which light coming from different wavefronts of same source superposed to give alternate perfectly dark and bright fringes of equal intensity that may or may not be of equal width. On other hand, diffraction is the result of interaction of light coming from different parts of same wavefront. Diffraction pattern we get consist of alternate dark and bright fringes if varying intensity with central maximal. Diffraction fringes may not be same width. The patterns and plot showing intensity variations are given. We have two types of diffraction, namely Fresnel and Fraunhofer diffraction. We know in the case of diffraction we will have a source of light, an obstacle or an aperture, and a screen in which we observe the diffraction pattern without lens. In the case of Fresnel diffraction, the source, slit and screen are kept at finite distances. Incident wave will not be planar, but spherical or cylindrical. Because of this, the phase of secondary wave will be different at different points of plane obstacle, and hence the resultant amplitude at any point on screen will be due to mutual interference if secondary wavelets. Even though experiment observation of diffracted pattern is easy, the analysis is complex. This type of diffraction is observed in zone plates. In Fraunhofer diffraction, source, slit, screen are at infinite distances. So, we need two lenses, one to make rays from source parallel and other to focus diffracted light from slit. The incident plane rays and secondary wavelets will be in phase at every point on the plane of obstacle. The Fraunhofer diffraction is easy to observe and analyze. An example is diffraction occurring in grating. Conditions for Fraunhofer and Fresnel diffraction are represented diagrammatically. In today's session, we studied about diffraction, Fresnel-Huygens theory, difference between interference and diffraction and types of diffraction. From next class, we will discuss about Fresnel diffraction. Thank you for today's session. See you in the next class.